All right, let's dive into one of the most fundamental, most powerful tools in all of machine learning, linear regression. Now, I know it might sound a little basic, but trust me, it's packed with some really clever ideas that are absolutely essential for anyone who works with data. I mean, we are just swimming in data these days, right? And in this giant ocean of information, we're almost always looking for the same thing, a connection, a way to predict one thing based on a bunch of other things. We want to predict a target variable by learning from a set of features. Think about it like this. How can we predict a house's price just by knowing its square footage and maybe its location? That's the kind of challenge we're talking about. So, how do we cut through all that noise to find the real relationship? Well, linear regression is our tool for doing that. It helps us find the right parameters. You can think of them as the settings or dials for our model that best describe the data. And when we say best, what we really mean is a model that makes the fewest mistakes. We're on a hunt for the simplest, most accurate truth hiding inside our data. So our first step on this journey is what I like to call the quest for best fit. We need a solid method to draw that one single line that best represents all of our scattered data points. So at its heart, what is linear regression? It's a method for prediction. We're trying to predict a target, let's stick with the price of a house, by looking at its features, like its size. The model does this by creating what's called a linear combination of these features. And our entire goal, the whole game, is to find the best parameters or weights for that combination. You know, you and I could both look at a scatter plot of data and just draw a line through it that looks pretty good. But how do we know which one is actually the best? How can we even measure goodness? Just eyeballing it is not going to work. We need a real mathematical way to define what the single best line actually is. And that brings us right to our second section, measuring the misses. See, to find the best line, we first have to agree on a system for measuring how wrong every other possible line is. Okay, so the core unit of our miss has a special name. It's called a residual, and it's super simple. It's just the vertical distance between a real data point and where our line predicted that point would be. Every single data point has one. It's our error measured one point at a time. But how do we take all those individual little misses and combine them into one single score for the whole line? Well, it turns out there are two main philosophies on how to do this. There's L2 loss, also called squared error, where you square each residual. And then there's L1 loss, or absolute error, where you just take its absolute value. Now, this might sound like a tiny, nerdy detail, but trust me, this choice has massive consequences down the road. And here's the crucial thing to understand. By squaring the error, L2 loss gets really angry about big mistakes. If your line is off by, say, 3 units for one data point, that single point contributes 9 units to your total error score. L2 has a very, very low tolerance for predictions that are way off base. Okay, so this is where that choice between L1 and L2 gets really dramatic. In a perfect world, our data is clean and nice. But what happens when it isn't? What happens when our data misbehaves? You know, in a perfect, clean data set, it honestly doesn't matter much which loss function you pick. The best fit line you get from L1 and the one you get from L2 are going to look almost exactly the same. Everything's great. But as we all know, the real world is messy. Real data is rarely perfect. It's got errors, it's got typos. So the true test of any model isn't how it does in a nice, clean lab, but how it holds up when things get messy. So what happens if we just add one problematic data point, an outlier? And then reality hits. Let's say we add just one outlier, a single data point that's way off from all the others. Could be a measurement error, could be a typo. It happens all the time. This one point is about to cause a whole lot of trouble for one of our models. And wow, this just shows the difference perfectly. Take a look at this data. After we added that one single outlier, the slope of the L2 line changed by a whopping 0.238. But the L1 line, it barely even budged, only changing by 0.029. The L2 model, because it hates large errors so much, gets dragged kicking and screaming towards that outlier, and it messes up the whole model. So the takeaway here is crystal clear. L1 loss is more robust, it's tougher, it's more resistant to getting yanked around by these wild outlier data points. And that is a crucial, crucial difference when you are working with messy, real-world information. Okay, so we figured out how to find the best line, and even how to protect it from outliers. But what if the real pattern in our data isn't a straight line at all? Well, this brings us to a very, very cool trick. This is probably the most common question I get. I mean, it's called linear regression, so it must only be for linear straight-line relationships, right? Nope. And this is the secret that makes linear regression so incredibly flexible. The model is linear in its parameters, those weights it's learning. It's not necessarily linear in its features, the actual data you feed into it. And that means we can play with the features before they even get to the model. We do this using something called basis functions. Now, that's just a fancy way of saying we can transform our input features first. For example, instead of just giving the model a feature x, we could also give it x squared and x cubed as new features. And by doing that, our linear model can suddenly fit all sorts of curves and other complex, nonlinear patterns. It's awesome. So, for our final section, we need to talk about giving our models some rules to live by. Because once we start using these super powerful basis functions, we run the risk of creating a model that's too complex. We need to teach it some discipline. This discipline has a name: regularization. And hey, look who's back, our two philosophies, L1 and L2. L2 regularization, which is also called ridge, adds a penalty that encourages all the model's parameters to shrink and stay small. But L1, or lasso, is a little more extreme. It can actually force some parameters to become exactly zero, which basically kicks irrelevant features right out of the model. So why do we do this? Because this discipline stops the model from overfitting. That's when it just memorizes the training data instead of learning the real pattern underneath. This helps the model generalize, so it can make much better predictions on new data that it has never, ever seen before. And there you have it. It starts out as just a simple line, but then we add a few clever rules about measuring errors, handling outliers, transforming features, and staying disciplined, and it becomes this incredibly powerful tool for learning from the past. And that really just leaves us with one big question, doesn't it? What patterns are out there in your world that we should ask it to predict next?